Okay, back after our little break there, and I believe where we left off was the idea of, say, using the solubility table to try to predict whether a precipitation or potential precipitation reaction will happen or not with two ionic reactants that are soluble in water. An example would be, say, barium chloride and potassium sulfate, which are both soluble in water. And the question might be, does this reaction occur, or what are the products? Well, since this reaction features two ionic reactants, it's a pretty good bet that it's a double displacement type reaction like we've been talking about, and that the cation and anion simply switch partners. So that would mean barium chloride and potassium sulfate will become barium sulfate and potassium chloride. And so that's what we have here. The formula for barium sulfate is just BaSO4 because barium is in group 2A, so it will have a +2 charge on it, and the sulfate ion has a -2 charge on it, so they will go together 1-to-1 in BaSO4. And potassium is in group 1A, so it has a charge of +1. Chlorine is in group 7, so it will have a charge on its ion of group number -8 or 7 -8, which is -1. And so +1 and -1 will go together in a 1-to-1 ratio. So the formula is KCl. But according to the reactants, we have 2 Ks and 2 Cls. So it's 2 KCl. Those are, at this point, the potential products. Emphasis on potential, because we haven't determined yet whether this reaction actually occurs or not. So these are the products we will get if the reaction actually occurs. How we tell whether the reaction occurs or not is to look up the two products in the solubility table. The solubility table says that most compounds involving the sulfate ion are soluble, with some exceptions. BaSO4, barium sulfate, is one of the exceptions. So BaSO4 is insoluble, and that means this is our precipitate. So we now know that this reaction does occur. And you should check the other possible product also, because, well, we know this reaction occurs, but every once in a while you might actually get two precipitates instead of just one. So we got to make sure whether this is also a precipitate or not. Most chloride compounds, according to the table, are soluble. And in fact, KCl, potassium chloride, is not one of the exceptions. So KCl is soluble. As I said in the last segment of the videos, all compounds involving metals from group 1A, which include potassium, are soluble. So just the fact that this compound has potassium in it tells you right there that it's soluble. So that will be aqueous. And so our molecular equation will be BaCl2 aqueous plus K2SO4 aqueous yields BaSO4 solid plus 2KCl aqueous. And we can now use that information to write the ionic and net ionic equations. Barium chloride, BaCl2, is soluble in water, and it is ionic because barium is a metal and chloride is a nonmetal. And if it's ionic and soluble, that means it will ionize in water. So barium chloride will consist of one barium ion, again with a charge of +2 because it's in group 2A, and it'll consist of 2 Cl- ions. Potassium sulfate will consist of 2 potassium ions with a charge of +1 each because potassium is in group 1A. And then the sulfate ion is also present. Remember that the potassiums will ionize from the sulfate ion, but the sulfate ion itself remains together because sulfur and oxygen are nonmetals, and so the bond between them is not ionic. So SO4 - 2, aqueous. These would all be aqueous. I because it's tedious to write the little AQ over and over again, I do have a habit of often dropping the phase label aqueous and just writing in a phase label if it's anything other than aqueous. And unless I tell you otherwise on a test or a quiz, I'm okay if you do that also. So basically, we assume everything is aqueous unless we state otherwise. So when we write the formula for BaSO4, we need to write in S for solid because that's not aqueous. And then when we write KCl, we get 2K plus ions and 2Cl minus ions. Those are both aqueous. So if you want to be lazy like I am, you can leave the little AQs out. For the non-ionic equation, we look through and see what changes and what doesn't. We see that the barium ions come out as part of barium sulfate, but the chloride ions come out as chloride ions, so that's no change. Those are spectator ions. They can be canceled. The K plus ions come out as K plus ions, so they can be canceled. But the sulfate ion comes out as part of barium sulfate, so that has to stay. And your net ionic reaction would be barium ions, and I decided to write the aqueous this time, plus aqueous sulfate ions yield barium sulfate solid. And again, that tells you anytime you get barium and sulfate ions together in solution at the same time, you will get barium sulfate solid forming. And it doesn't matter how the barium and sulfate ions get into solution. This could have been barium chloride, but it could have been barium nitrate or barium acetate or some other soluble barium compound. The sulfate ions could come from potassium sulfate, but they could come also from sodium sulfate. That's soluble and gives sulfate ions, or any number of other compounds. And an example of when you don't have a reaction would be what happens if you say try mixing sodium nitrate and potassium chloride in water. The potential products would be sodium chloride and potassium nitrate. All of the ions here have charges of +1 or -1. So everything here is 1 to 1. So it's actually already balanced. I'm putting a question mark, though, over the arrow because we don't know yet whether this reaction actually occurs or not. In order to find out, we have to find out whether the two products are soluble. Hopefully you already know that sodium chloride is soluble in water, but just in case, you could look at the solubility table under chlorides, and you'll see that most chlorides are soluble, and sodium chloride is not an exception, so therefore sodium chloride is soluble. And as I said a moment ago, all sodium compounds are soluble anyway. So definitely soluble. What about the potassium nitrate? Well, the table tells us all nitrate compounds are always soluble, and there are no exceptions, so potassium nitrate is soluble. And also, all potassium compounds are soluble since potassium is in group 1A. So yeah, you bet potassium nitrate is soluble. So we've got two soluble ionic components, or products rather, and that means that there is ultimately no reaction here. And if you don't believe me, you can try writing out the ionic and net ionic equations. So for our molecular equation, we have the equation we just wrote. I'm persisting in putting the question mark over the arrow, though, because again, we just established that this reaction doesn't actually occur. So we don't want to just write the equation without the question mark, which would imply that it does occur. So, so we're going to investigate and prove whether this reaction occurs or not. Sodium nitrate is a soluble ionic compound, so it will actually consist of sodium ions and nitrate ions, both aqueous. Potassium chloride is a soluble ionic compound, so it will consist of potassium ions and chloride ions, both aqueous also. Sodium chloride is a soluble ionic compound, so it will consist of sodium ions and chloride ions, both aqueous. And potassium nitrate is a soluble ionic compound, which will consist of potassium ions and nitrate ions, aqueous. And then you go through and you look for the spectator ions. And look what happens. They're all spectator ions. Sodium plus comes out as sodium plus. NO3 minus comes out as NO3 minus. And in fact, as I mentioned a few minutes ago, sodium ions and nitrate ions will always be spectator ions. And in fact, potassium ions will also always be spectator ions. And sure enough, they come out as exactly the same as they went in. So spectator ion, and the chloride ions will not always be spectator ions, but they are in this case. And so they're spectator ions too. They're all spectator ions. They all cancel out. And when it comes time to write the net ionic equation, there is literally no reaction because there's nothing left. So that proves that the reaction actually doesn't occur, in case there was any doubt. And so I'm going to put an X through the arrow just to make the point that that doesn't actually occur. So what you've really got is just a bunch of ions sitting around in solution: sodium ions, nitrate ions, potassium ions, chloride ions, and nothing can come together with anything else in solution in a way that will keep them together. And so nothing happens. Okay. Okay, well, another thing that we can look at here is the idea of acid-base reactions. We've already mentioned acids and bases. We've seen at least one example of an acid-base reaction. And it's probably time that we should at least mention, at least in passing, what acids and bases are and what happens when they, react with each other. We will cover acids and bases in much more detail later on in the semester, if we get that far. But for now, we'll just do a sort of a quick overview of acids and bases. An acid is basically, the formula for an acid is the H plus ion plus some anion. The anion could be chlorine, in which case you get HCl, which is hydrochloric acid, or the anion could be something like the nitrate ion, in which case you get HNO3, which would be nitric acid, and so on. And the identifying chemical characteristic of acids is that they release H plus ions when you put them in water. They ionize to release H plus ions. Sometimes that's written as H3O plus, because what happens when you release an H plus ion in water is that it will combine with water molecules to form the hydronium ion, which is H3O plus. So sometimes it'll be written as H plus aqueous, and sometimes it'll be written as H3O plus. And so again, some examples of acids would be HCl, HBr, HNO3, H2SO4, and so on. A base is actually a little more broadly defined than acid. And a base is usually, at least at this point in our investigations, a base will usually take the form of a metal hydroxide. So a metal ion plus the hydroxide anion. And what they do in solution is they increase the hydroxide ion content in water. And you may notice that the characteristic property of acids is that they release H plus ions in water. And the characteristic property of bases is that they release, or at least increase, the OH minus concentration in water. And if you take H plus and OH minus and combine them with each other, what you get is water. And that's why acid-base reactions are often referred to as neutralizations, because the characteristic ion of an acid, which is H plus the characteristic ion of a base, which is OH minus, will combine to form something that is neither an acid nor a base, or in other words, it's neutral, which is water. So if acid-base reactions can also be thought of as neutralizations. Some examples of metal hydroxide type bases would be sodium hydroxide, potassium hydroxide, lithium hydroxide, magnesium hydroxide, calcium hydroxide. Any metal hydroxide, even lead hydroxide, would be considered a base. Also considered bases, though, would be ammonia and related compounds known as amines. Ammonia has the formula NH3, and ammonia counts as a base because it removes H plus ions from water. So when you put ammonia in water, what you get is an ammonium ion. And when you take an H plus away from water, what's left? OH minus. So by increasing the OH minus concentration when you put it in water, that's what qualifies ammonia as a base. Also, carbonates and bicarbonates, or hydrogen carbonates, are considered bases. Sodium carbonate has the formula Na2CO3, and if you combine that with water, what you get is carbonic acid, which is a weak acid, and sodium hydroxide, which is a strong base. And so overall, the result is increasing the basicity of water. Of course, NaOH is an ionic compound, so it's really present as Na plus ions and OH minus ions in water. And so sodium carbonate increases the OH minus concentration in water. Sodium hydrogen carbonate does much the same thing, only it combines with one water instead of two. And you get, again, carbonic acid and one sodium hydroxide this time, but that increases the hydroxide ion concentration in water, and so sodium bicarbonate is a base. Okay, in acid-base reactions, like I said, the acid gives up an H plus ion, which is taken in by the base. Like, for instance, in this case, you can think of the acid as giving up the H plus ion, which the base OH minus takes in to form H2O. Acids and bases can be considered strong or weak depending on the degree to which they ionize in water. So some acids ionize completely in water, and they are considered to be strong acids, and the same with bases. There's a table on page 187 of the textbook that lists out the strong acids, and there are only about 7 or so strong acids. So it's probably best to just memorize the strong acids, and then it's safe to assume that any other acid will be a weak acid. And there are literally millions of weak acids, so a vast majority of them are weak. And so if you put hydrochloric acid in water, HCl aqueous will completely ionize into H plus aqueous plus Cl minus aqueous. Total and complete ionization. And that's what makes it a strong acid. All other acids are weak. That would include things like hydrofluoric acid or acetic acid or phosphoric acid, and also chlorous acid and hypochlorous acid, and like I said, literally millions of others. And these ionize much, much, much less than 100%. And when a reaction does not go to completion, we use a double-headed arrow to sort of indicate that it's kind of going in both directions at once and it never reaches full completion in either direction. So if we were to take the weak acid HF, aqueous, in water, we would find that it partially dissociates or ionizes into H plus F minus, but not fully. And in fact, a vast majority of the hydrofluoric acid would be present as intact HF molecules, and only a few percent, usually less than 1%, would be found as independent separate ions. Whereas in the hydrochloric acid, 100% of them will be present as separate ions, and about 0% will be left as intact molecules. Okay, oh, and I already had that down here. If you want to write in the H2Os, you can do that. And so hydrofluoric acid in water will react to form H3O plus and fluoride ion. That's equivalent to what I wrote up here, except up here I just wrote aqueous instead of writing in the H2O, but it really amounts to the same thing. Sometimes in reactions that don't go to completion, like the ionization of a weak acid in water, we will make the backward arrow much bigger than the forward arrow to sort of indicate that most of it will actually be found in this form at any given point rather than in this form. But you don't have to do it that way. Strong bases are also relatively few in number. The group 1A hydroxides, so sodium hydroxide, potassium hydroxide, lithium hydroxide, cesium hydroxide, and so on. And two of the group 2A hydroxides, strontium hydroxide and barium hydroxide. Those compounds are the only strong bases that exist, and there are literally millions of weak bases. So if you just remember the strong bases, and it's safe to assume that anything else you encounter would be a weak base. So the weak bases would be all of the other metal hydroxides, like, for instance, calcium hydroxide, aluminum hydroxide, copper hydroxide, both copper hydroxides, copper 1 hydroxide and copper 2 hydroxide, all weak bases. Lead hydroxide, silver hydroxide, all weak bases. Also, ammonia and carbonates are all weak bases. Yeah, so there are a lot of weak bases out there. The reactions of weak bases in water are also equilibrium reactions. So calcium hydroxide in water the calcium hydroxide would partially dissociate into calcium ions and hydroxide ions. But again, I'm making the backward arrow bigger just to remind us that most of it will be in this form rather than that form. Ammonia and water, again, will combine and you'll get ammonium ions and hydroxide ions, but again, most of it doesn't react. And sodium bicarbonate and water will react to form sodium hydroxide, which again is present as sodium ions and hydroxide ions, and also carbonic acid, which is unstable in water and immediately dissociates into carbon dioxide and water. That's why carbonates basically tend to fizz when you put them in water or expose them to an acid for that matter. So this is a weak base. In each case, you usually get less than 1% of the compound actually reacting at any given time, and about 99% or more would be found as the unreacted reactants. And as we've seen actually in the past few examples, water can react as an acid or a base. Essentially, water will be the opposite of whatever you're reacting it with. So if you are combining water with an acid, then water acts like a base. And you consider basically a base is something, as we mentioned a moment ago, a base is something that takes in H plus ions. So the water ends up as H3O plus because it took in the H plus ion from the HF, leaving the F minus behind. So water was acting like a base here. But if you come over here, water is acting like an acid, because an acid is something that donates an H plus ion to something else, and a base is something that takes in an H plus ion. So here you've got the water giving an H plus ion to the NH3, which becomes NH4 plus, and what's left behind of the water after it gets rid of an H plus is OH minus. So water was an acid here. So water has what's known as an amphoteric property, which means it can act as an acid or a base, basically whatever the other stuff isn't. Mix, an acid with water, water will act like a base. Mix a base with water, water will act like an acid. And again, it can do both of those things because it consists essentially of acid and base. H2O consists of H plus, which is the characteristic ion of acid, and OH minus, which is the characteristic ion of bases. And that's why water can basically be whatever the other stuff isn't. Acid-base reactions, as I already mentioned, are called neutralizations because they tend to produce products that are neither acids nor bases, or at least weaker acids and bases than what you started out with. So the reactants will be an acid and a base, but actually, if one of the reactants is H2O, it's not considered an acid-base reaction. So technically, this reaction here, well, ammonia with water, that's not considered an acid and a base, even though the water is technically acting like an acid. Don't ask me why. So the reactants would be an acid and a base, and the products in most cases would be some form of salt and water. But in this case, by salt, what we mean essentially is an ionic compound. It's kind of a circular definition because salt is actually defined as an ionic compound that can be created by the reaction of a strong acid and a strong base. So saying that, a salt is defined as the product of an acid and a base is, kind of goes around in circles. So we can consider effectively that a salt is just an ionic compound, because there are really not very many ionic compounds that cannot be created by the reaction of a strong acid and a strong base. So some examples of acid-base reactions would be hydrochloric acid and sodium hydroxide. And notice that acid-base reactions are double displacement reactions. So HCl and NaOH will produce NaCl and HOH, which is better known as water. So there's your salt and there's your water. Hydrochloric acid and magnesium hydroxide will become magnesium chloride and HOH, or water again. So MgCl2, magnesium chloride, and HOH, or water. When balancing it, it turns out that each magnesium hydroxide requires 2 HCl's and produces 2 H2O's. But that's just a matter of balancing. And in a moment, I see we're over time, so I'm going to stop this segment here. But in a moment, we'll come back and we'll see the molecular ionic and not ionic reactions for those equations.